Thanks for coming to the session today. My name is Joe DeVore, and I've been working on build grants for the last 4 or 5 years. We have a lot of planners that come to us using VISSIM and kind of ask us, how can we get more benefit out of our traffic operations, our safety analysis, and really try and get some of these benefits that go into the BCA higher so that we have a better chance of winning these mega projects and compare against other projects throughout the nation. So this project that we worked on was up in Moorhead, Minnesota. It's about a population of 40,000 people up in the northwest corner of Minnesota. It's also right across the river from Fargo, North Dakota, which is a much larger municipality. But it's kind of the same MPO area, where if you include some of the smaller cities around it, it's about 233,000 people in that metropolitan area. The main interstate that goes kind of south of the metropolitan area is I-94. This is one river crossing. And then there's 3 river crossings in downtown where the red box is, between Moorhead and Fargo. Center Street, Main Avenue, and First Avenue. And so all 3 of these roadways are major components of this study. One of those being US Trunk Highway 10, which actually makes a jog in downtown Moorhead. So there's a lot of turning movements going through the downtown section, and there's also some major railways that go through the city. So this is a major rail connection between Duluth, Twin Cities, and the West Coast. We get about 60 to 75 trains using 2 train tracks through the city. So if you break that down, that's about 3 an hour that are going through the downtown area. And this creates a major disruption in the town, major queuing, and a lot of delay, especially on that trunk highway segment, where it does have to cross the tracks at grade. There's 9 total at grade crossings throughout the downtown area, and it's about 1.5 miles long was the section we did in VISSIM, kind of 3 corridors, each 1.5 miles long. So a little bit of background on kind of the build discretionary grant application process. The US DOT puts out this application process to try to find projects that have a significant impact on a local or regional location. They're usually in the 15 to 20 million range. You're trying to get those big projects where a city or a county couldn't pull together funds to fund this on their own. There's a total of about 900 million available for these build grants. About 25 million per project or less. That's kind of the upper bound, and then only 90 million can be awarded to single states. So they do try and spread this around the country. The last couple of years, they've been making a big push to get to about 50% to rural areas for rural projects. So what that means is it's under 200,000 population. The Fargo-Moorhead area is at 233. So unfortunately, we didn't meet that category to get into a rural application. But we're hoping that some of the analysis we can pull from other benefits can put this one over the edge. So the application was due in July 15th this year, and we're expecting them to be awarded around November 12th. Sometimes they release them a little early, but usually they push that deadline. So our modeling process was a lot different than previous build grants that Moorhead submitted for this project. So what they're looking for is a grade separation of one of these crossing routes, so that it goes in under the rail, both of the railroads. We wanted to change up the modeling process to really look at the complete daily benefit, so a 24-hour model. Previous models really only quantified the AM and PM peak benefits and just kind of blankly factored that out throughout the day. We really wanted to look at all of those crossing benefits because of those 3 to 4 trains an hour. Even in the AM, you're going to have some major benefit of being able to go in under the tracks and not have to stop for a 5 to 6 minute train. We wanted to implement a dynamic traffic assignment that would mimic ITS systems, where if there was a train crossing, drivers would have that knowledge and be able to go to the under rail grade separation. We wanted to have kind of an origin destination calibration. Since it was a grid network, we didn't want to run into kind of that turning movement gridlock where you end up getting a block queue, which ends up blocking another queue, and you end up crashing your model. So we really wanted that origin destination volumes going into our analysis. And then we also wanted a very good visual of the results. So we had some of our graphic designers put together a 3D model of all the buildings in Moorhead, which we were able to take to stakeholder meetings and really show these different options of the project. So our study approach, we had a very robust data collection. We did the origin destination assessment using streetlight data. We developed a VISSIM model and calibrated it. Traffic projections development took some time. With the Moorhead downtown area, it's pretty well built out right now. It's an older downtown, so there is some redevelopment happening, but we're not seeing major growth. However, we have seen major train growth, especially back during the Bakken oil boom. There were probably close to 120 trains going through Moorhead at that point. We also wanted to look at some alternative analysis when we did put in the grade separation. Could we do some road diets to some of the 5-lane sections going through Moorhead? And then finally, we developed a benefit cost analysis for the build grant. So our data collection did include about 20 turning movement counts. We had 8 daily counts kind of around the downtown area. You can see the 3 major east-west routes. And then we did take train data collection points as well, looking at the time of blockage, how many trains, when they came during the day, also that we could put this level of detail into our VISSIM models. So looking at some of that train data over the years, since Moorhead had developed build grants, I believe 3 previous times, they have a lot of this train data year after year of, how bad is the problem in Moorhead. And really we saw kind of between 60 to 70 trains per day on average, looking at this yearly data. There are 2 tracks, the KO, which is the northernmost track, and then the Prosper, which is the southernmost track. And they are kind of unbalanced as far as train volumes using them. Sometimes the trains came when the other one was going, so you kind of double down on some of those queues. The worst case scenario is a 5-minute train one way, with one coming the other way directly after it, which would cause major queues on Trunk Highway.
What are the speeds of the train going through? Is it fast or slower?
Since it's going through a downtown area, I believe it's around 15 to 20 miles an hour for the trains going through. So it's about a 5 to 7 minute train going through here. And they're long trains too, I believe. We had about a mile in the model. So big trains and very slow. So looking at the time of day when the trains were coming, they did try to not come during AM and PM peak hour. You'll kind of see that there's a high number of them kind of overnight, and then in the middle of the day with the traffic volumes in that kind of blue color behind. So you can see that when you have major vehicle spikes, Luckily, we don't have major train spikes at that same time, so we're able to kind of balance the existing traffic. Even though there is a problem, it's managed somewhat today, and it's not kind of the worst case scenario. When we looked at how long that train was crossing, our average was between 3 to 5 minutes for blocking a specific crossing. When you add in the gate time, the arm coming down, it was usually 5 to 7 minutes. The previous model was a little bit higher, and then they do have some switching maneuvers where the trains end up blocking a certain crossing for up to, I believe, 10 minutes. So those happen maybe 3 to 5 times a day, usually outside of those peak hours. So when you start kind of taking that blockage delay and picturing it of what the daily impact is, for the existing conditions, it's almost 1/4 of the day there's a train going through downtown Moorhead, blocking at-grade crossings. When we started projecting traffic, looking at maybe a 1% growth in that train data, you're up near 30% of the day. So almost 1/3 of the day you have a train making at-grade crossings through downtown Moorhead. So I talked about streetlight data, being able to take that turning movement data and really assign where that traffic's going. We didn't want to use static turning movements in our VISSIM model, so we wanted to create kind of that origin destination matrix around our study area. So we were able to use streetlight data with MnDOT's access to it. So we had real robust OD data. We ended up doing exterior points, both origins and destinations, and then interior zones to kind of balance out traffic where it was going in downtown. This created about a 50 by 50 origin destination matrix for a 24-hour model. That was a lot of balancing. So we kind of grouped this data. Streetlight already groups it into kind of an early AM, AM peak, midday, PM peak, and then late PM. We kind of took that and said those origin destination routes are going to be pretty similar during those periods, and instead we're going to take those percentages and then balance out the turning movements throughout those sections. So really we only created the 5 50 by 50 origin destination matrices. And then we also looked at middle filter analysis for the 3 north-south routes connecting all 3 of our east-west routes, 8th Street, 11th Street, and 14th Street. We wanted to really see what traffic was using those, where they were going, and understanding that so that when we did have that 11th Street grade separation, we understood what volumes were shifting from the other routes to use that grade separation. And so talking about the matrix, this is a screenshot of one of those 5 peaks. We ended up having all of the origins and destinations summed up. We did a sum of squares in Excel to try and limit that error, comparing back the vehicle inputs of all of the incoming traffic and outgoing traffic that we had from our turning movements, and then balance that through our origin destination from streetlight to kind of limit out the error. And for most locations, we were within probably 300 to 500 vehicles for a five-hour period. So when we balance that back to the turning movements, our movements were off by about 5 to 10 at the most. So we felt that we had a really good balanced set of data going into VISSIM that we could use, and then we did back check this against those turning movements by kind of using some features in VISSIM. So we started out with our turning movement counts. We had our northbound, southbound, eastbound, westbound movements for each intersection, for each hour of the day, so 24 hours worth of it. We then took that, and in the VISSIM model, we created connectors for each of those turning movements. So usually you only have your left turn connectors and your right turn connectors. We actually broke the links going through the intersections, so those through movements also had a connector number associated with them. And when we look back, for each of those turning movements, we had a connector number associated with that. So what we were able to do with that then is when we pulled out the routing out of VISSIM, now we had a link sequence for each of those OD routes going through the model. And we were able to do index functions and VLOOKUPs to take our streetlight data that we had for each hour and then compare that back to the turning movements and then take specific link sequences and change them up to balance out the turning movements. So that was kind of a trick that we learned in VISSIM, was really using those connector numbers to back check to our turning movements. I did talk about the middle filter. We had 3 major north-south connections between all of our east-west traffic. These were the grade crossings. 8th Street today is used the most. It's got about 5,000 to 6,000 for traffic. 11th Street's around 15 to 2,000, and then 14th is around 3,000. It's kind of hard to see the numbers there. But this was really important because 11th Street is actually the least used roadway today, but that was where the grade separation fit the best in downtown, and it was kind of a central location, so we felt that we pulled traffic from both 8th and 14th kind of going through the study area. Talked a little bit about the growth implications before. We ended up assuming about a 0.5% growth factor for this area. Since downtown was kind of redeveloping, this was kind of a punt for really doing an in-depth forecasting, but we wanted to feel that we had some growth involved in downtown and that we felt comfortable with if we built this grade separation, traffic would still flow through downtown. So kind of looking at our no-build conditions in our VISSIM model, you'll see a train pop up here in the lower left crossing, and we did about a 20-second link evaluation where you'll start to see some of the queuing that happens when the left turn signals go red for the entire length of the train. And so we have signalized intersections at all of these major points that do have those preamps in there which stop those movements into the train so that we don't have queuing back out from those links. But what that causes is quite a bit of queuing along 8th Street, quite a bit of queuing along Main Avenue coming back out. The southern route of Trunk Highway 75 coming into the model, that backs up right away. And this is at about 4 or 8 times speed, so this is about that 4-minute crossing. And you can see all the red that's happening on these major trunk highway routes coming in. So Trunk Highway 10 comes into the study area, comes up to 8th, jogs, and then goes out Main. And although it does recover after the train goes through, it usually does take 2 to 3 cycles for it to fully recover. So when we start looking at that daily graph of what's happening, you can really see all of these spikes throughout the day. Every time a train goes through downtown Moorhead, you're doubling or tripling that delay per vehicle during these train events. And so we ran the model with trains. That's those red marks where you see those jumps. And then we wanted to see what happens if there were no trains or everything was grade separated. What really is the impact of all the trains in the model? And so this bottom line is just from the traffic. So you can really see that difference. There's a lot of benefit if we can get people using this grade separation going through downtown Moorhead and really not queuing from when a train goes through. I talked a little bit about the routing before. During a train event, we wanted to have this be kind of an ITS feature where we could put up advance warning. When a train hit a detector, drivers would know to use the 11th Street grade crossing instead of any of the other at-grade choices at 8th or 14th. And so we wanted to adjust these routes only during train events so that when there weren't train events, people still took their more direct route. And so we get to call out Levi here. We kind of ran into a problem where I knew I was going to have to do some coding. It ended up being a lot easier than I thought with the route choice method option in the partial vehicle routes. And so Levi kind of helped us with developing a formula where when a train came into the study area, tripped a detector coming into the area, the routing would change dynamically where drivers would know to use the grade separation. And so instead of kind of guessing at what that traffic shift would be to the grade separation, we were actually able to dynamically go through and see what that volume shift was between our no-build and build model by using this dynamic routing during a train event. And so just calling out that highlighted, really all this code is saying is when the train is on detector 500, the routing will be 5423. So that was all the volume using 8th, 11th, and 14th. When it wasn't, it would just be its normal volume using that route. So we did have partial routes in both the no build and build for all these red arrows. They were not a permanent redistribution and didn't account for kind of backtracking where it would be kind of a backwards movement. It was only for movements that were using the major roadways going through the study area, which we had the existing OD routing for. So when we started looking at our build grant results for putting in this grade separation, we did notice quite a bit of this delay getting cut by about a third or half of those spikes. And so for our 2019 field conditions, where it was our balanced volumes, our existing train data from 2019 and our existing volumes, we had about an 8% delay benefit throughout the day, and then about a 4.5 reduction in total vehicle hours traveled. This was about 155 hours saved per day of just people not waiting at tracks and queues. When we started looking at 2045 scenarios, you can see that big increase in kind of that PM midday peak where it's not fully recovering after a train event. A train would go through, you'd still have some of those queues, and then you'd have another train go through and you wouldn't get rid of those queues and they just compound and really start adding to the delay throughout the day. So we had an even better delay benefit, about an 18% delay benefit for our 2045 forecasts. That was about a 1% growth for traffic volumes and a 1% growth for train volumes. We did a couple other scenarios where we looked at that 0.5% growth for traffic volumes. We looked at a 2% growth for train volumes. And when we went up to about a 2% growth for train volumes, it absolutely broke the model because you'd get to the PM peak and these would just compound to where they couldn't recover at all and would end up causing gridlock in our models. So we really kind of went to our stakeholders and said, you know, that there is a limitation to the model. It might work, but really with a 2% growth rate for the trains, we would expect some pretty bad conditions in the future, which our model just can't look at. So I did talk about that 0.5% growth. So we did some additional model runs after the build grant was submitted with kind of additional trains. We wanted to look at that high mark for trains that had come through. And you can see that the lines get a lot closer together. We used a little bit less for traffic, but we still had a much bigger existing benefit. So more trains cause more delay. If you give them a grade separation, it's going to be a lot more benefit when we were looking at that. And so we were at about 266 hours saved. And then for that 2045 scenario with just the 0.5% growth, we were in that kind of 700 hours saved per day range. And so when we kind of compared what we had submitted for the build grant and then what we had for kind of our sensitivity scenarios, there weren't too many differences other than that existing when you looked at your total VHT saved. And we had a little bit more benefit, and if we were to go back and submit for the build grant, we probably would have used this because there's a lot more benefit attributed to existing conditions than it is to future conditions. And so just a video of our build conditions. You'll see as the train comes into the model here that this left turn queue is going to stop queuing, and all of these vehicles are going to go up to 11th Street now. And so we had some dynamic or adaptive signal timing where our maxes jumped up by about 50% for these major movements, having that additional traffic growth coming in. And you'll see that there's hardly any queuing along Main Avenue down here. There's still a little bit of queuing on US 75 and to the north, but these left turn movements, these through movements, clear within one cycle. So it's a lot better running model. You're not seeing those really long kind of compounding queues that we were seeing in the no build. Another big factor for our build grant application was quantifying the safety. It wouldn't be a presentation by me if I didn't talk about SSAM a little bit. So we did use SSAM to really quantify the rear end merge and crossing conflicts, kind of on a quantitative level between no build and build. From the pictures, you don't see a lot of change. There's a lot less impact along this kind of left edge where those queues were extending across into Fargo. The build scenario really did fix some of those queuing issues. And so we ended up with a 2019 change in conflicts of about 15 to 20%. Crossing conflicts are usually your more dangerous ones, your left turning conflicts, your right turning conflicts. So we did end up using both the crossing conflict percent reduction and the total reduction in our BCA calculations. For the 2045 models, just based on that compound queuing, we saw a real big reduction in our total conflicts, which ended up creating a pretty big safety benefit. So when we start looking at bringing this safety benefit into our build grant BCA application, we did separate it out by safety, and then we looked at the existing crash data for the last 5 years and really broke up those crashes by rear ends, crossings, and lane change type conflicts, so that we could really target those percent reductions in our conflicts and really attribute them to only those types of crashes. And then we quantified them based on the 20 years in our safety benefit, and ended up with a total benefit of around 24 million for that 20-year benefit. And so as we brought in both the travel time and the safety data into our BCA calculations for the build grant, we have a comparison between our values in 2019 and then the values in our previously submitted build grant in 2017. And the big one here is travel time savings. So that's that VHT that we were quantifying in the model. And it's almost 3 times the value that we calculated in 2017. That was due to kind of that bigger model, looking at 24 hours, and really that in-depth ITS routing that we had implemented in the model. So all those results go into fuel savings, pollution reduction, and it helps raise those benefits as well, having a very good kind of traffic operations model. And so for our final BCA, something a lot different than the way I had done MnDOT BCAs is the 7% discount rate. So what that really does is you have to see benefit in your existing conditions, because that 7% compounds over 20 years. So whatever your benefit is 20 years down the road, it's a lot less using a 7% discount rate, where MnDOT uses about a 2% discount rate. So that was where our future models didn't have as much benefit as our existing models did. And if we had to redo it again, we'd look at some of those different scenarios for quantifying our existing benefit. For some totals over that 20-year horizon, over 4 million vehicle hours travel would be saved with this grade separation project, and about 575 crashes would be reduced just by eliminating that congestion in the downtown area. We did look at several build alternatives. Because our model was operating so good during those build operations, we looked to downsize, going from 5-lane to 3-lane for some major routes. We again used our VISSIM model for this, since we had kind of the entire downtown area. We were able to test these very easily. We also looked at removing a few right turns, and then if we had space, to use a shared use path instead of one of the lanes on 11th going in under the bridge, so that we had a multimodal connection that was also grade separated. Kind of looking through these, I'm going to go through fast because I know I'm running out of time. We did kind of go through these kind of separately, recommending if they worked or not. So Main Avenue, kind of to the east of the study area, we showed that that was able to be changed from a 5-lane section to a 3-lane section for the road diet. 11th Street wouldn't be recommended reducing it to a 3-lane section, because the queuing was impacting adjacent intersections. The 3-lane section along 11th north of 1st and south of Main, so kind of outside the study area, that wasn't recommended, just because of the lane usage coming into the intersections. Center Avenue had already been kind of identified as a road diet, going to a 3-lane section, and we kind of confirmed that through our analysis. Again, the conflicts weren't a major factor for this either, so we felt that it'd still be a safe 3-lane section. Whereas some of the other locations, when you change it to a 3-lane section, you're adding to the congestion, and going through these intersections, we saw a 20 to 30% increase in conflicts at those intersections. So that was another reason why we didn't recommend 3-lane sections in a few locations. We did end up looking at all of the alternatives from that safety perspective, and we were able to highlight which alternatives caused a major increase in those conflicts. And then the delay, which ones created a delay increase versus our base build model down here. We went through a couple of different options for lane usage, getting rid of those right turns. Kind of gave the stakeholders those options so that they could kind of decide on their final vision for this grade separation project. And then with that, just kind of a summary, you know, a larger area equals a larger benefit. Anytime you have queuing or a project going through a downtown area, you really want to quantify all the traffic coming in and using that downtown area. The visualizations were very key in talking through those alternatives with the stakeholders. They could kind of see the queuing that could happen. Really, if they wanted to trade in that 5-lane section for moving vehicles to the 3 lanes for more sidewalk space, ability to put in multi-use trails, was really key in kind of ironing out that final vision for the project. Being able to have that static and dynamic routing combination without using scripting was very key. So having that option to use those partial routes to kind of route traffic inside an origin destination matrix. And then finally that SSAM providing a site-specific safety benefit versus using CMF factors is really a detailed way to understand what types of crashes that your improvements are reducing, and gives you a better feeling for the safety of the project as well. So with that, guess we're open to questions.
Yeah, I got actually 2 questions.
Yeah.
One, how would you use VISSIM AR for this? Just curious. If you had access to VISSIM AR, how would that change the presentation?
Yep, so hopefully we would be able to import our buildings into VISSIM AR.
Yeah.
Going out and talking it through with both the stakeholders and the public. We have had some public meetings for this as well. Just being able to show them the project, having that existing traffic, seeing those queues when the trains go through, and then being able to slide it over and really see that benefit between the 2 videos I showed in kind of real time would be a major push for this project. People already know it's a bad area out there. They don't want to drive through downtown when there's trains going through. But just being able to visualize that in front of them, it would be a huge benefit.
Good to hear. Second question, I don't notice too many heavy vehicles in the model, but as far as the more the specialized vehicles like a school bus, a transit,